the nozzles, diffusers, mixing chambers, as well as the heat exchangers. Now, the steady flow energy process actually has been derived from the following sketch, where you have energy at the inlet and energy leaving. So the energy analysis states that energy at the inlet is equal to energy at the outlet of the system. Now, if you scroll down, on the left-hand side, we have energy at the entrance and energy at the exit. But we have put a potential energy at the inlet plus the kinetic energy at the inlet plus flow work or flow energy at the inlet plus internal energy at the inlet plus heat. The heat is in bracket. Why is bracketed? Because heat normally is heat lost, and if heat is lost, it's negative. But we will see when we start solving the problems, which is equal to the potential energy plus kinetic energy plus flow energy plus internal energy plus work done. Work done can be for a turbine or work input by a compressor, but we will explain that further. So now when we expand from here, in most cases, the potential energy in steady energy in the SFEE, because this is also this steady flow energy equation is also called SFEE in short. So in most cases, the potential energy is very, very small as compared to other parameters or variables in this equation. So if the potential energy is very small, then PE1 and PE2 are going to cancel each other. They're going to cancel each other, which means that PE1 and PE2 is equal to 0. Or sometimes, if the device is horizontal, it means that the potential energy is going to be at inlet is going to be the same as the potential energy at the outlet, which means P1 and PE2 is equal to 0. So don't be surprised when you don't see this PE or the potential energy when we write down our steady flow energy equation. Now, the kinetic energy, we know kinetic energy is what? It's half c squared, half c squared. Now, we don't use V here because V in thermodynamics stands for volume. So velocity, we are going to use the word C. So this C stands for velocity. In other words, we have got potential energy that we are going to scratch off when we solve problems, plus the kinetic energy, which is velocity squared divided by 2, plus P1, V1, which is the flow energy, plus U1, which is internal energy, plus Q. Now, P1, V1 plus U1 is equal to enthalpy. You can see on your right-hand side here, number 9 here, it says that H, which is a specific enthalpy, is given by internal energy plus flow energy. Now, we are going to, when we analyze all these devices that we are going to analyze today, we are going to apply this formula for all of them. Now, we will see how the formula is going to change with respect to each device. So let's start with the first one. The first one we're going to discuss, I said, is a turbine. The question is going to be, what is the function of a turbine? Because sometimes things can go wrong in the exam, and if you don't know a function of a turbine, you won't even see if your answer is wrong. The function of a turbine is simple. The function of a turbine is to convert kinetic energy into work. The function of a turbine is to convert the kinetic energy, the kinetic energy into work. So we start with the first one. The first one is going to be a turbine. A turbine. Now, with the turbine, we said that we are interested in work output for the turbine, nothing else. We're interested in work output. So I'm going to draw a schematic diagram of a turbine, and then after I will write down the steady flow energy equation for a turbine. Is in kilojoules per kilogram because everything now is specific. So at point number 1 here is inlet, and point number 2 is outlet. So at point number 1 we have the following properties. The first one is going to be enthalpy at point 1 at the inlet. We are going to have temperature at the inlet. We are going to have velocity at the inlet. We are going to have what else? Internal energy at the inlet. We are going to have pressure at the inlet. We are going to have a specific volume at the inlet. Similarly, in the outlet, we are going to have the same properties: H2, T2, C2, U2, P2, and specific volume at 2. Now we apply the steady energy equation, SFEE, for a turbine. We start by saying that C1 squared divided by 2 plus enthalpy at 1 plus Q is equal to kinetic energy at the outlet plus specific enthalpy at the outlet plus work output. So this formula is SFEE for a turbine. Very, very important if you can write it down. So the main focus for a turbine, we are focusing on the work output, while we don't ignore other properties. Now, Q in the turbine, when you answer the questions, you must be very, very careful when you read the questions. When the question says an adiabatic turbine or isentropic, adiabatic or isentropic. Isentropic process or adiabatic process is that process that does not to enter or leave the system. In other words, for adiabatic system or isentropic system, Q is equal to 0. This is very, very important. It's not always the case. Some questions will tell you that the Q is given as this much, and normally Q is the heat lost. There's no way in which when the turbine is working, heat is received. Always heat is rejected or lost. That is always the case. So please, when we read the question, the most important part of that one is whether the turbine is an isentropic turbine or adiabatic turbine. If that is the case, it means that Q is equal to 0. Heat is not allowed to enter or to leave the turbine. So the first one is the steady flow energy equation for the turbine is C1, or kinetic energy at 1 plus enthalpy Q, and kinetic energy at 2 plus enthalpy at 2. So the second one is going to be a compressor. The function of a compressor is simple, is to increase the pressure of air. Function of a compressor is to increase the pressure of air. Right, so the second one is a compressor. Compressor. And the function of a compressor is to increase the pressure. But now a compressor does not actually give work output. It requires work input in order to work. Unlike a turbine gives us work output. But a compressor, in order for a compressor to work, we must first give it a work input. So before I forget, when you do your calculations, and the question says, calculate the work done by the compressor, sorry, by the turbine. By the turbine, your work output. Your work output is positive, always positive. When you do your calculations, you find that the work output is negative, you must know that your calculations are wrong. So the work output is always positive for a turbine. The question says, for the following turbine, calculate the power or the work output. Your work out is always positive. But when we are dealing with a compressor, the compressor, because it's requiring work from us, the work input for the compressor is always negative. So when you do your calculations and your work input is positive, you must know that you made a mistake. Please don't mix the two. Turbine, positive, compressor, negative. So let me draw a schematic diagram of the compressor so that I can also apply a steady flow energy. The schematic diagram of a compressor is similar to that of a turbine. The difference is the direction of flow. We have work input, sorry, for the compressor. And then we have one at that point here, we've got two. This that C1 squared over 2 plus enthalpy at 1 plus Q is equal to C2 squared divided by 2 plus enthalpy at 2. We have all of these properties. You calculate work input, your answer is going to be negative. So for online test, if your answer is negative, you must put negative. Because even if the answer is correct and you put the wrong sign, the system is going to mark it wrong. I repeat, for online test, if your work input is negative, please put a negative sign. Because if you put a positive sign, it means now we are not dealing with the compressor, we are dealing with the turbine. That is very, very important. So heat here, again, it depends. If the question says that the compressor is fully insulated, it means that Q is equal to 0. But in most cases, Q also be given, because during compression, heat increases in the compressor. And if heat increases, then it's going to escape. And then we will end up having that Q. So this is SFEE for a compressor. The difference between a compressor and a turbine is work input and work output. That is the second one. So the third one is going to be a nozzle. In engineering, the function of a nozzle is to increase the pressure of a fluid at the expense of its pressure. Number 3 is the nozzle. The function of a nozzle in engineering is to do what? To increase the velocity or to accelerate the working fluid at the expense of pressure. What happens is that at the beginning of the nozzle or at the nozzle inlet, so this is a nozzle. At nozzle inlet, which is at point number 1, the pressure is high, P. The pressure is high, and velocity, C, velocity is low. Now, as the fluid continues to move along the length of the nozzle here, the pressure decreases and the velocity increases. At the outlet, the pressure has gone down, has dropped, but the velocity has increased. Hence, we're saying that the function of a nozzle is to increase or accelerate the speed of a working fluid at the expense of its pressure. Pressure decreases, velocity increases, that's the nozzle. Now, a nozzle has a cousin. The cousin of a nozzle is called a diffuser. A diffuser does the opposite. A diffuser does the opposite. It actually decelerates the speed of the working fluid. Where we have 1 here, we've got 2 there. At point number 1, velocity is up, is high, and the pressure is down. But at the outlet, the pressure is up, velocity has dropped. This is the nozzle. Now let's apply the steady flow energy equation on the nozzle and see how it goes. So we will have C1 squared over 2 plus at 1 plus Q is equal to C2 over 2 plus H2 plus work input or work output. So let's see. Velocity, yes, this is a nozzle. We will have a velocity at the inlet, which is going to be very, very small. And then the highest velocity is at the outlet. Enthalpy is there because there's pressure, there's volume here, and internal energy. There is enthalpy at 1, and there's also enthalpy at 2. Q, in most cases, the question will tell you that for an adiabatic nozzle, adiabatic nozzles, it means that this nozzle is fully insulated. Therefore, heat is not allowed to enter or to leave the nozzle. This is an adiabatic nozzles. Otherwise, Q will be given. So for W, it's always 0. There is no work because there's no mechanical parts. There's no moving parts in the nozzle. There's no moving parts. Therefore, the steady flow energy equation for a nozzle remains this one. This is a steady energy equation for a nozzle. In most cases, or sometimes you'll be told that the velocity at the inlet is negligible. In other words, very, very small. Therefore, if it's small, it means that this part is going to fall away. Therefore, you have H1 plus Q is equal to C2 over 2 plus H2. Now, because you know a function of a nozzle, when you do a calculation, you are always expecting that your C2 is always higher than your C1 if you are dealing with a nozzle. Your C2 is always higher than your C1. That is the function of a nozzle. But for diffuser, the opposite here happens. Your C1 is always higher than your C2 because during the length, as the fluid travels along the length of the diffuser, the pressure increases and the velocity drops. You can't have a increased velocity and the pressure at the same time. No, they always go opposite ways. So for a diffuser, C1 is always greater than C2. That is why I'm saying that when you do your calculations, please make sure that you check your answers. You should be able to see that, no, my answer doesn't make sense. How come that my C1 is greater than C2 for a nozzle? That's why the first thing that I do is to discuss the purpose or a function of each machine. Compressor, I said the compressor is to increase pressure. Increase the pressure of a working fluid. Compressor is like a pump, but the pump is working with incompressible fluids, but the compressor works with compressible fluids. The nozzle, the function is to increase velocity or accelerate the velocity of the working fluid. The turbine is to do what? Is to convert the kinetic energy into mechanical output. Now, after the nozzle, now we have what we call the mixing chambers. Mixing chambers. Have you ever seen a mixing chamber? Two fluids of different temperatures or different masses or whatever, but I'll explain. What is a mixing chamber? For example, at home, we do have a mixing chamber. A shower is a mixing chamber because you have cold water coming from one side and hot water coming from one side. You mix both to get your final result. And again, they also mix, the companies that use mixing chambers are automotive companies that do spray painting, where they mix a couple of the paints to have the final product. So those are the mixing chambers. So schematically, this is how we represent our mixing chamber. So at 1, we have got mass flow rate at 1 and enthalpy at 1. And then at 2, we have got the mass flow rate at 2 and the enthalpy at 2. At this point here, we have got mass flow rate at 3 and enthalpy at 3. So the energy in, we said that the energy in is equal to the energy out for a mixing chamber. Energy in is going to be the mass flow rate at 1 multiplied by enthalpy at 1 plus the mass flow rate at 2 enthalpy 2 is equal to the mass flow rate at energy analysis. Mass analysis is simple. Mass analysis is going to be M1 plus M2 is equal to M3. So from here, we can continue and say M1 H1 plus M2 is equal to, M3 is equal to what? M3 is M1 plus M2 multiplied. So you calculate the mass flow rate at 3 or at 2 or at 1. It depends on the question. But for mixing chambers, this is how you have to understand the energy analysis. This is energy analysis. Mass analysis is simple. Mass analysis is going to be mass at 1 plus mass at 2 is equal to mass at 3. But I forgot with the previous devices, I forgot to address the issue of mass balance. For all of them, is the same. For compressors, turbines, then we say that ME, mass at the inlet, is equal to the mass flow rate at the outlet. In other words, we say that mass flow rate is going to be density at 1 multiplied by velocity at 1 multiplied by area at 1 is equal to, at outlet, you have density at the outlet, velocity at the outlet, and area at the outlet. So this is that I've covered is for a turbine, a compressor, a diffuser, and a nozzle. This is the mass analysis for those. Mass analysis, this is energy analysis and mass analysis. But for mixing chamber, this is energy analysis, this is mass analysis. The last one is, what is the last one? The last one is the heat exchangers. Number 5 is heat exchangers. That is the last one before now we start solving problems. The heat exchangers. Heat exchangers. What is the function of a heat exchanger? It is to exchange heat. You might not know what a condenser is, but the simple one that you must all know is a radiator in a motor car. That is a heat exchanger. So let me draw a sketch of that so that we can analyze the mass analysis as well as the energy analysis of a heat exchanger. So for heat exchanger, I'm going to draw a sketch. Schematic diagram here. This is a condenser. The function of a condenser is condense a steam into liquid. So what happens here, we've got cooling water at 1. And then we've got cooling water at the outlet, cooling water number 2. And then we have steam inlet at number 3. And then we have steam outlet at number 4. So what happens that the steam enters at 3 as steam, but now the cold water, flowing through the condenser here, cold water is going to condense that steam. Right, so we have got steam entering here as steam. Now, once the steam comes into contact with the, so at point number 4, you have water. Point number 4, you have water. And then point number 3, you have steam. So we say that the heat lost by the steam is equal to heat gained by cooling water. Here you have cooling water at point number 1. Cooling water at a very low temperature, let's say 15 degrees Celsius. And at the outlet here, you can even as high as 8 degrees Celsius because it has absorbed the heat from steam. So this is a condenser. The mass flow rate, the mass balance for a heat exchanger or for a condenser is, we say that M1, the mass at 1, plus the mass at 3, mass flow rate at 3 is equal to the mass flow rate at 2 plus the mass flow rate at 4. This is the mass balance for a heat exchanger, for this particular heat exchanger. Now the energy analysis or balance, we say that energy into the condenser is equal to energy out of the condenser. So energy in is going to be mass flow rate at 1, multiplied by enthalpy at 1, plus inlet again is a 3, is inlet. M3 multiplied by enthalpy at 3 is equal to outlet, you've got M2 enthalpy at 2 plus M4